Welcome back, class. It's good to be with you. We're going to cover Chapter 17 of Whitlock and Schluter, Regression. My goal is to do this in two parts. First part, we'll cover the background concepts. The second part, we'll do one in-depth example. Okay. The way I want to do this from the standpoint of the lecture notes is I've got a historical example here. We'll discuss that in class. And I'd also like to discuss linear models in class in order to frame regression within a broader framework. But for our purposes, I want to zoom right in to this simple linear regression concept. Okay, so the idea is that we have some data, two numeric variables that we could find a correlation coefficient between. So we're thinking an x explanatory and a y, a response variable. They have some type of relationship. We're interested in those with a linear relationship, at least right now. As we'll see later, this can be generalized to any form of nonlinear relationship that we could describe with an equation. So it is extremely powerful. But to get there, we need to start with the simplest. So there's your linear concept. Now, we're going to go back to your Algebra 1, the simple y equals mx plus b slope-intercept form of a line. Okay? So in the theory, we take the basic line, but as we saw from our example, the points are off of the line in real data. There's some form usually there's multiple forms of variation from that line. So we describe those with an additional random variable. We're calling it epsilon. Those are going to be the residuals. Okay, what do we come up with? Well, we come up with simply a line. So we're going to call the actual phenomenon y, and then the sample, not the sample observation, the estimate is going to be y hat. So these individual observations are the y's, that would be y1, and then this little value down here on the line, that's going to be y hat 1. The difference between those two guys, that's the epsilon. So that'd be epsilon 1. All of these epsilons are called residuals. They'll be part of our analysis. Okay. Now, using calculus, it can be shown that this is the best estimate. Best meaning it minimizes all of the residuals according to a certain definition called least squareds. So this is least squared regression, where the slope is the sum of the squares xy divided by the sum of squares x. These are quantities used in correlation, chapter 16. The intercept is very simple. It's, you can see, mean of y minus slope times mean of x. What that says is the point x bar, y bar is always on the line. So if we just use our y equals b naught is the slope plus, that b naught's the intercept, plus the slope is b1 times x. Since this point, x bar, y bar is on the line, we can solve this equation for b naught, and that's where we get that form. So the real work is getting the slope. And if you'd like to ask during class for a little more indication of why that's the case, please do so. Okay, here's those definitions, though they were covered in 16. Now, why do we do this? Well, formally speaking, there's two primary reasons. And these get at a very broad class of mathematical approaches to all kinds of phenomena. But here we see them in regression. So one is prediction. We'd like to know what's going to happen in the future. So if we can build this model, no matter whether it really captures the underlying mechanism or not, We just want to predict the future. Secondly, we don't really care about prediction. We just want to know what's really going on. Some things are linearly related, and this can help us to find that linear relationship, or as I stated before, we'll extend beyond that. Okay. Now, in doing regression, as we've seen with other tests, there are assumptions. Okay? We're going to focus in on these last two, which I will combine as one. But first, the xi are held fixed. So basically what we're thinking there is, given this value of x, what are the possible values of y? Graphically speaking, by that I mean, given that we are here on the map, boom, then what's the value of y? In this case, we went a little bit below the line. On a subsequent draw, maybe it's going to go farther, okay? Maybe above it, somehow different. So there's a conditional assumption. Not a big deal for our purposes. We're assuming that the errors are random. In other words, they're independent of each other. They don't depend upon other neighboring observations, but each observation is taken independently of the others. And we're also going to assume that when we're taking these measurements, that any error in the measurement is negligible. Maybe present, but it's so small relative to the other variation that it's insignificant. Okay. Those are all pretty reasonable assumptions. Everybody tends to take those for granted. These two are the ones we're going to be concerned about. And they are the variation in y, these observations in the response, is the same no matter what value of x you're at. And furthermore, those errors, which is equivalent to saying the behavior of y, is normally distributed. Let me show what I mean by these two. Okay, back here, we're saying that for this given x here, the amount of variation in the y is the same as for this given x over here. Okay, so you're looking for about the same variation all the way through. This is the same assumption we made in ANOVA. All right, the other assumption is not only is it the same, but it's normally distributed. So you can envision that we'll take at this point x here, there's a little bell-shaped curve whose center is right there on the line. If I take and rotate this guy counterclockwise, then we'll have this observation. Here's the bell-shaped curve. If this number was, let's say, 10, then this would be centered here. Oh, and maybe that one came out at, say, 20. It would be centered at 20, okay, with some measure of variation. Okay, now let's consider the results. The primary result that we want to focus on is for making inference. And it is the observation that the slope follows a normal distribution if the assumptions are met. That is, the normality on the residuals assumption. With the normal slope, then, the population mean is the mean of the true line that gives rise to this phenomenon. And the standard error is this guy, sigma over rad SSX, where this sigma is the assumed, it's the common error or standard deviation of the residuals. Under that, then, we can take if you do a null hypothesis, then we typically consider the population parameter to be 0. Instead of using a z-score, we're going to use a t, because we are going to estimate this residual standard error with little s, sample standard error. So we have a statistic minus a parameter divided by a standard error. That gives us a statistic we can test with. If we don't want to do that, we can calculate confidence intervals with this standard error. We're good to go. the degrees of freedom on the t-statistic is a simple n minus 2. Now, how good of a fit do we have? Well, for one, we can calculate this residual standard error. For two, high correlation coefficients indicate good fit. Using the coefficient of determination, like we saw in ANOVA, that gives us an information about the proportion of variation explained. And I haven't stated this yet, but this is the formula for calculating the residual standard deviation. This is the actual point minus the point on the line. Square those, add them together, and then divide by n minus 2, take the square root. Lastly, as I stated before, these things can be generalized to many, many other things, including more than one explanatory variable. In fact, you can even do more than one response variable. It's very, very generalizable. This is the most powerful tool of statistics, and I hope that we can get to showing some of these extensions at the end of our time on this topic.